In this video, we're going to cover section 1.5.4 on second-order reactions type 2. Let's consider the following elementary reaction step, where two reactants, A and B, are involved in the formation of product P. And so to differentiate type 2 from type 1, type 1, we had a single reactant species. In type 2, we have two different reactants reacting. So if the reaction is first order with respect to A and B, the corresponding rate law expression is as follows. We have the overall rate of the reaction equal to the rate constant K1 multiplied by the product of the concentration of A and the concentration of B. Now the reaction, as we've seen previously, can also be written in terms of the time derivative of the reactant concentrations. So in each case, the overall rate of the reaction can be written in terms of the consumption of both A and B, dA dt and dB dt. As a result, the rate of consumption for the reactants is equal, such that the difference between A naught and some concentration of A at time t is equal to B naught minus some concentration of B at time t. And so we can rearrange this expression for the concentration of B. Now, because there are two reactants present, we need to establish a relationship between A and B, meaning we need to know that as A is being consumed, how much of B is being consumed. And in this particular example, it's a 1-to-1 ratio, that as 2 moles of A is being consumed, 2 moles of B would also be consumed. But the starting concentrations of A and B may be different. The initial concentrations may be different. And as a result, during the course of the reaction, you may have more of one species over another. That's very typical of reactions that we generally look at. So this expression here, where we include this delta term, it's signifying that the concentration of B is equal to delta, which is the difference between B naught and A naught, plus the concentration of A. Now that we've defined this particular relationship, we now obtain a solvable differential rate expression. And so the rate expression is as follows, that dA dt is equal to minus K1 times the concentration of A times the concentration of B, and this is equal to the following, where we're making this substitution for the concentration of B with this new term delta plus the concentration of A. Rearranging this expression as we've done previously, we now have this as our integral. Now, this integral also has a solvable solution, and it takes on the form the integral of dx over x bracket c plus x. And the solution to this, a little bit more complex than what we've seen previously, is minus 1 over a constant ln c plus x over x. Using this solution to the integral, the integrated rate law expression becomes the following. Here's our solution with our two limits. And the right-hand side is simply, as usual, minus K1t. So we will end up with this particular expression, and we can simplify this expression somewhat to give us the following. And then this can further be rearranged by substituting back in for delta, which was the initial concentration of B minus the initial concentration of A. And so this here is the solution for the integrated rate law for a second-order reaction type 2. Again, with a slight rearrangement, we end up with our integrated rate law for second order reaction type 2. And so for a second order reaction involving two reactants A and B, each with a first order dependence, a good linear fit to the experimental data will be observed for a plot of the ln of this particular quotient against time if there is a strong association between these two terms. And the slope of the linear fit corresponds to the product of the rate constant and this term delta, which is the difference between the initial concentration of B and the initial concentration of A. You can also calculate the half-life with respect to either species A or species B using this particular expression. But I'm going to leave that for an upcoming assignment. So with this, we've covered 4 different models that we typically use to assess the chemical kinetics of reactions. We've covered zeroth, first, second, type 1, and type 2 order reactions. We have integrated rate laws for each of these 4 scenarios. If you have any questions about second order reactions type 2, or any questions about integrated rate laws in general, by all means, send me an email. Thank you.